Hello students, today we are going to discuss about the actuators. So the objectives of today's lecture are to know the various types of actuators which are used in process control systems. The number of actuators are used like classic DC motors are there, geared DC motors are there, industrial servo motors, stepper motor, solenoid, pneumatic and hydraulic actuators. So basically we'll just see what is actuator first. An actuator, it is a component of a machine or system that moves or controls the mechanism or the system. So an actuator is the mechanism by which a control system acts upon an environment. Or you can see it is an device which requires a control signal and source of energy. So here we can see a sensor, whereas it takes or it converts the interesting useful energy into electric data signals. On the same time, actuator, it converts that electrical data signal into interesting useful energy. So these both of these like sensor and actuators are not same. You can consider an example. If a valve is used to control fluid flow, some mechanism must physically open or close the valve. So if a heater is to warm a system, some device must turn the heater on or off or vary its excitation. So these are some of the examples or these are some of the requirements for an actuator in the process control loop. So you can see that actuator it takes on many diverse forms to suit the particular requirements of process control loops. Upon receiving a control signal, the actuator it responds by converting the energy into mechanical motion. The control system can be simple like a fixed mechanical or electronic system, a software based example like printer drivers are there, robot control systems are there, a human or any other input also. So some of the examples are given for an actuator like solenoids can be used, electric motors can be used, hydraulic cylinders can be used, pneumatic cylinders or motors can be used. So the types of actuators are like hydraulic, pneumatic, electrical and thermal or magnetic or mechanical. Today we are going to discuss about the three types of actuators, hydraulic actuators, pneumatic actuators and electrical actuators one by one. So the first one that is electrical actuators, you can see here a motor driven based rotary actuator. The second one that is stepper motor linear actuator. So here an electrical or electric actuator, it is generally powered by a motor that converts electrical energy into mechanical torque. The electrical energy is used to actuate equipment such as solenoid valve, which controls the flow of water in pipes in response to electrical signals. It is considered as one of the cheapest, cleanest, and speedy actuator types available. So many types are there, right from your solenoid to your all these motors, electrical motors also. So that we are going to discuss today. So the first one is solenoid. It is simple electromagnetic device that converts an electrical signal into mechanical motion, usually rectangular in, or you can see in a straight line. It is an elementary device that converts an electrical signal into mechanical motion. It consists of coil and plunger that is freestanding or spring loaded. Sometimes it is. It has very short stroke that is the length of the movement also. And in this, the coil which is used, it will have some voltage or current rating and maybe DC or AC. It is used when a large sudden force must be applied to perform some job. Also, it is used in electromagnets, inductors, antennas, walls, etc. The applications, if you see for the solenoid, they are differ in numerous types like medical, locking systems, industrial use, the bottom line, and automotive also. So here you can find out the coil which is used. It will have some voltage or current rating and maybe DC or AC. The solenoid specifications, it includes the electrical rating and the plunger pull or push force when excited by a specified voltage. And this force may be expressed in newtons or kilograms in the SI system and in pounds or ounces in the English system. So some solenoids are rated only for intermittent duty because of thermal constraints. So in this case, we have considered the maximum duty cycle. Suppose percentage on time or time to total time will be specified. So here the solenoids are used when, as I told you, that is a large sudden force must be applied to perform some job. So a solenoid is shown here, which is used to change the gears of the two position transmission also that we are going to see. So whenever it is energized and whenever it is unenergized, you can find out that is how it works. So as I told you, that is whenever a solenoid is used to change the gears of a two position transmission, it is shown over here. That is with the help of SCR, it is used to activate the coil over here. So here you can find out a solenoid which is activated with the help of the SCR. And by that way, the conversion of the energy will be done. We can find out different types of solenoids over here. That is AC laminated solenoid is there, DC C frame solenoid is there, DC D frame solenoid is there. Then the next is linear solenoid and rotary solenoid. So many types are there depending on the application you can select. The second one, that is electrical motors. So electrical motors are the devices that accept the electrical input and produce a continuous rotation as a result. So motor styles and size vary as demands for rotational speed, that is revolution per minute or RPM, starting torque, rotational torque, and other specifications vary. There are numerous cases where electrical motors can be employed as actuator in process control. So probably the most common control situation is where motor speed drives some part of a process and must be controlled to control some variables in the process. The drive of a conveyor system, for an example. The types of electrical motors, as we all know, that is AC, DC, and stepping motors are there. So we are going to discuss one by one here. So the rotation of a DC motor, it is produced by the interaction of two constant magnetic fields. It is as shown in the figure. One type of DC motor that employs a permanent magnet, that is PM, to form one of the magnetic fields. The second magnetic field is formed by passing a current through a coil or wire contained within the PM field. This coil of wire, which is called as armature, is free to rotate. Now you can notice that the coil is connected to the current source through slip rings and brushes, which are called as a commutator also. But the slip rings are split so that the current reverses direction as the armature rotates. So we can find out the rotation of the same, that how it occurs. You can see in the figure here, you can notice that the north, that is N, and the south, S, poles of the permanent magnet and the armature are not aligned. Thus, there will be a torque driving the N from N and the S from the S. Therefore, the armature will rotate counterclockwise, which is shown in the figure. If it were not for the split slip rings, the armature would rotate until N and N, and of course S and S are aligned, but the split rings are arranged so that the current direction and therefore NS direction of the armature reverses as the alignment occurs. So here you can find out. Actually, the armature current is not determined by the coil resistance because of a counter EMF which is produced by the rotating wire in a magnetic field. Thus, the effective voltage which determines the current from the wire resistance and Ohm's law is difference between the applied voltage and the counter EMF which is produced by the rotation. So you can find out many DC motors use an electromagnet instead of permanent magnet to provide the static field. The coil which is used to produce this field, it is called as a field coil, and this kind of DC motor is called as a wound field motor. So the current from for this filled coil can be provided by placing the coil in series with the armature or in parallel, that is shunt. In some cases, the field is composed of two windings, one of each type. This is called as a compound DC motor. So here you can find out some configurations for the DC motor. The characteristics of DC motor with a field can you can consider like the first one, that is a series DC motor or series field. So if you see for this motor has large starting torque but is difficult to speed control. So good in applications for starting heavy, non-mobile loads and where speed control is not important, such as for quick opening valve. So for that type, the series field will be used. The next one we are having, that is shunt one. So this motor has a smaller starting torque but good speed control characteristics produced by varying armature excitation current. If you find out the applications where it is used, that is speed is to be controlled, such as a conveyor system. In that case, the shunt type motors can be used. The compound field, the third one, this motor attempts to obtain the best feature of both of the two previous types. So generally, starting torque and speed control capability fall predictably between the two pure cases. So these are the three configurations of the DC motor: series, shunt, and compound. So the use of DC motors in the control system ranges from very low energy, delicate control applications to heavy duty control applications in elevators and vehicles also. So in general, the permanent magnet types are used for the motors of less than 10 horsepower and wound field types for units up to about 100 to 200 horsepower. So control of speed and torque of these large machines require very high power DC electricity. So such power is derived from the power electronics devices described earlier. And in general, if you see, the three-phase AC power is rectified using a switching technology to produce the required high voltage and high current DC electricity also. Now come to the next one, that is AC motors. So the basic operating principle of AC motor still involves the interaction between the two magnetic fields. But in this case, however, both fields are varying in time in consonance with the AC excitation voltage. So therefore, the force between the fields is a function of the angle of the rotor, but also the phase of the current passing through the coil. There are two basic types of AC motors: synchronous and induction motor. So the primary motors for the application to the control industry is the induction motor. So in synchronous motor, the AC voltage is applied to the field coils, which is called as a stator. In an AC motor, this means the magnetic field is changing in time in phase with the impressed AC voltage. Then the armature, it is called as the rotor for AC motors, is either a permanent magnet or a DC electromagnet and possesses a fixed magnetic field. So the primary motor for application to control industry is the induction motor. So you can find out this one, that is a simple synchronous motor with two poles and permanent magnet rotor. So a four-pole motor would have a rotor with two N and S bars for the rotor and four poles to the stator. The speed of rotation, that is Ns of a synchronous motor, is related to the frequency of the AC excitation and the number of poles by Ns is equal to 120 F by P, that is known to you. So this is the simple AC motor with a permanent magnet rotor. So here you can find out, that is the speed of rotation, that is Ns of a system or of a synchronous motor, how you can relate with the F and P. So here it is written Ns is equal to 120 F divided by P, which is in RPM, where F is the excitation frequency in Hertz and P is the number of poles. So synchronous motors can be operated using single phase AC, but such units are used for only very low power and suffer from very low starting torque also. So when operated from three-phase AC synchronous motors can be operated at very high power up to 50,000 horsepower. Now you can see for the induction motor over here, these are characterized by a rotor which is neither permanent magnet nor a DC excited electromagnet. Instead, current induced in the coil wound on the rotor generates the interacting magnetic field of the rotor. So this current is induced from the stator coils. So in the figure also you can find out it illustrates the basic concept. So you can see that the AC field of the stator produces a changing magnetic field passing through the closed loop of the rotor. So if you see the Faraday's law, it teaches us that this changing flux will introduce or it will induce current in the loop. This in turn creates a magnetic field in the rotor coil, which interacts with the field of the stator. So the bottom line is that the torque exists on the rotor because or it is caused by these two fields. So single phase induction motors are there, three phase induction motors are there. So if you see the single phase inductor motors are used for the applications or relatively for low power, say less than 5 horsepower. Such motors are typical of those found in household applications. For example, for higher power, we use three-phase AC excitations. Such motors are available up to 10,000 horsepower. So in a control environment, we want to have a control over the speed of the motors, and the inductor motor speed is dependent upon the AC excitation frequency. Now you can find out this is AC motor control with a variable amplitude, variable frequency circuit using power electronics. So it provides a typical scheme where the three-phase AC that is at 60 Hz is rectified to produce a variable amplitude DC voltage by using SCRs with variable firing angle from the control circuit. This voltage is filtered and then applied to a IGBT based inverter whose purpose is to produce a variable frequency AC voltage. The diodes across each IGBT provides for current flow in reverse of the IGBT. Of course, the sequence and speed of the switching provided by the control circuit determines the frequency. So the circuit could equally well use GTOs, MOSFETs, or even BJT devices also. Now coming to the next one, that is stepping motor, easily interfaced with digital circuits, so has increased importance in recent years. It is a rotating machine that completes a full rotation by sequencing through a series of discrete rotational steps also. And the latest step, thus the continuation rotation is achieved by the input of a train pulses. So you can find out the rotational rate is determined by the number of steps as revolution and the rate at which the pulses are applied. A driver circuit is necessary to convert the pulse train into a proper driving signals for the motor. So one example is like a stepper motor has 10 degree per step and must rotate at 250 rpm. What input pulse rate in pulses per second is required? So we can find out here a full rotation revolution has 360 degree. So with 10 degree per step, it will take 36 steps to complete one revolution. Thus, 250 revolution per minute into 36 pulses per revolution. Revolution get cancelled out and you will be getting 9,000 pulses per minute. Therefore, you can see like in pulses, if you want to convert, it will be like 150 pulses. This is the an elementary stepping motor, which is shown in the figure. The operation of stepping motor, it can be understood from the simple model, which is shown in the figure, which has 90 degree per step. In this motor, the rotor is permanent magnet that is driven by a particular set of electromagnets and in the position which is shown, the system is in equilibrium and no motion occurs. So here the switches are typically solid state switches or devices such as transistors, SCR, tracks can be used, and the switch sequencer will direct the switches through a sequence of positions as the pulses are received. The four positions of elementary stepper motors are shown over here. The next pulse will change S2 from C to D, resulting in the poles of that electromagnet reversing fields. And now, because the poles north-south orientation is different, the rotor is repelled and attracted so that it moves to the new position of equilibrium. That is which is shown in the figure B. So similarly, you can find out for the next rotations. Then we are going to discuss about the pneumatic actuators. The actuators often translate a control signal into a large force or torque as required to manipulate some control element. So the pneumatic actuators is most useful for such translation, and the principle is based on the concept of pressure as force per unit area. If we imagine that a net pressure difference is applied across a diaphragm of a surface area A, then a net force acts on the diaphragm. So pneumatic actuators, they converts energy formed by vacuum or compressed air at high pressure into either linear or rotatory motion. Rotary motion. The pneumatic rack and actuators are used for wall controls of water pipes. They are they quickly respond to starting and stopping signals also. So two of them are shown over here. The power source does not need to be stored in reverse for the operation. And the last, that is pneumatic actuators enables large forces to be produced from relatively small pressure changes. For example, pneumatic brakes can vary responsive to small changes in the pressure applied by the driver, and it is responsible for converting pressure into force also. So as I told you, the pneumatic actuator is most useful for such translation, like it translates a control signal into a large force or torque as required to manipulate some control elements. So here you can find out F is equal to A into P1 minus P2, whereas F is a force which is in Newton, P1 minus P2. This is the pressure difference which will be in Pascal. Then diaphragm area in meter square, that is E. If we need to double the available force for a given pressure, it is merely necessary to double the diaphragm area also. So very large forces can be developed by a standard signal pressure ranges, that is of obviously from 3 to 15 psi, and many types of pneumatic actuators are available, but perhaps the most common are those associated with control valves. So we can see here that is the pneumatic actuator. In the figure, it is shown a direct pneumatic actuator for converting pressure signals into mechanical shaft motions. So the action of a direct pneumatic actuator, it is shown over here. The condition in the low signal pressure state where the spring is maintains the diaphragm, and the it is connected control shaft in the position is shown over here. The pressure on the opposite side, that is spring of the diaphragm, is maintained at the atmospheric pressure force on the diaphragm, forcing the diaphragm and connected shaft down against the spring force also. So in this figure, again, you can find out spring as the hole is shown with the notation H, and diaphragm and pressure input is shown. It shows that like in this case of maximum control pressure and maximum travel of the shaft, the pressure and the force are linearly related, as we know, and the compression of the spring is linearly related to the forces also. Next, that is the shaft position is, as I told you, it is linearly related to the applied control pressure. How to find out it? That is delta x, that is shaft traverse, which will be in meters, is equal to what? A divided by K into delta P. whereas delta P is what applied pressure gauge pressure that is in Pascal, and A is the diaphragm area, and K is the spring constant that is N divided by M. Now, one more thing, we are having a reverse acting pneumatic actuator also. So, a reverse actuator which is shown over here, it moves the shaft in the opposite sense from the direct actuator but obeys the same operating principle. Thus, the shaft is pulled in by the application of a control pressure. So, this is the reverse acting pneumatic actuator. When we want to motion to occur under low shaft load, we simply increase the pressure in the actuator via regulator in this case, and the regulator allows more gas from a high pressure reservoir to enter the actuator. So this increases the diaphragm force until it is able to move the shaft. Suppose the shaft is connected to a very high load, that is something requiring a very large force for movement. In principle, it is simply a matter of increasing the pressure of the input gas until the pressure diaphragm areas equals the required force. Now let's see one example based on this. Suppose a force of 400 Newton must be applied to open a wall. Find the diaphragm area if a control gauge pressure that is of 70 kilopascal must provide this force, which is nearly about 10 psi. Then we must calculate the area from F is equal to A into P1 minus P2. Now here we have to find out this where our applied pressure, that is P1 minus P2, because a gauge pressure is specified over here, then you can find out A is equal to F divided by P, whereas F is what? 400 Newton, which is given. Then P, 7 into 10 raised to 4 Pascal. You can find out easily A is in meter square, that is 5.71 into 10 raised to minus 3. It is about 8.5 centimeter in the diameter. Then let's see for hydraulic actuators. A hydraulic actuator, it consists of cylinder or fluid motor that uses hydraulic power to facilitate mechanical operation. So you can find out here an oil-based hydraulic actuator is there, a radial engine acts as an hydraulic actuator is there. The mechanical motion which is converted to linear, rotary or oscillatory motion over here. So since liquids are nearly impossible to compress, hydraulic actuators exert considerable force. The actuator's limited acceleration restricts its usage also. So we have seen that there is an upper limit to the forces that can be applied using gas as the working fluid. Yet there are many cases when large forces are also required. So in such cases, a hydraulic actuator may be employed. So the basic principle, if you see that the basic idea is same as for the pneumatic actuator, except that an incompressible fluid is used to provide the pressure, which can be made very large by adjusting the area of the forcing piston, that is even. So the basic idea, as I told you, it is same as for the pneumatic actuators. Only one thing is different, that is except for that the incompressible fluid which is used to provide the pressure, which can be made very large by adjusting the area of the forcing piston, that is even. So let's see. That is here one example we are having which shows the F1 force, applied piston force, forcing piston area, that is A1. Similarly, FW, that is force of working piston, and A2, or you can find out the working piston area, another one. And pH is given, that is hydraulic pressure, which is in Pascal again. Okay, so this is for hydraulic actuators. Let's see. Here also you can find out into this, that is pH, that is hydraulic pressure. It is given by pH is equal to F1 divided by A1. whereas F1 is the applied piston force and even is the forcing piston area. And this pressure is transferred equally throughout the liquid. So the resulting force on the working piston will be what? Fw is equal to pH into A2. So whereas Fw is what? Force of working piston, and A2 is what? Working piston area. Thus, the working force is given in terms of the applied force by Fw is equal to A2 divided by A1 into F1. That we have to remember. Now, let's see one example based on this. Here it is asked to find the working force resulting from 200 Newton applied to a 1 centimeter radius forcing piston if the working piston has a radius of 6 centimeter. It is asked to find the hydraulic pressure also. So a hydraulic actuator, it converts a small force F1 into an amplified force, that is Fw. So we can find the working force from like Fw is equal to A2 divided by A1 F1. Okay. So, or you can easily convert it into W is equal to R2 divided by R1 square into F1, whereas R indicates the radius. So, we are having it as a 6 centimeter and 1 centimeter, that is working piston. It has a radius of 6 centimeter and 1 centimeter radius forcing piston. So, you can find out F1 is given over here. So, Fw can be easily find out like 7,200 Newton. Thus, the 200 Newton force provides 7,200 Newton of force. Okay, conversion of force. And the hydraulic pressure is given. pH is equal to Fw divided by A2. Fw we are having 7,200 Newton divided by pi into 6 into 10 raised to minus 2 meter square. So here you will be getting this pressure which is approximately as 93. Now one more thing is given, a basic control wall cross section. The direction of a flow is important for the proper value action over here. So wall body and seat are shown over here. The flow in and flow out also. So here the purpose of this is, as I told you, to regulate the flow rate of fluids through the pipes in the system. And the last, a pneumatic actuator, which is shown over here, it is connected to a control wall, and the actuator is driven by a current through an I to P converter over here. So this can be used, a typical control wall, which is using a pneumatic actuator attached to the drive the stem and hence to open and close the wall. So there are three basic types, as I told you, control walls whose relationship between the stem position and flow rate, it is shown in this figure. Okay. So today we have discussed about all the actuators which are used in process control system, like three types we have discussed: electrical actuators, pneumatic and hydraulic actuators.